Section 2.2 is called the derivative, and it actually is going to look and feel quite similar to what we did in 2.1. So the first thing that you're going to notice is you're going to notice a definition for derivative. The derivative of the function f at the point x equals a is defined as f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h, provided the limit exists. And if the limit exists, we say that f is differentiable at x equals a. So the first question of the day for you is, what did we call this in section 2.1? Because we saw this before.
Slope of the tangent line.
Slope of the tangent line. We had one more name of it too. Any others? There's one more name we had. This is the one we've used the most frequently.
Slope of the secant line.
Nope, the secant line's close to this one. It doesn't have the limit part. It's close. Velocity, or instantaneous velocity more specifically, right? This was also instantaneous. So if they all have the same formula, then all three of these phrases mean the same thing, right? They all mean derivative. So derivative, instantaneous velocity, and slope of the tangent line are all exactly the same thing. They're thought of in a little bit different ways, used in a little bit different contexts, but they're found the same way. They're the same thing. And then this word differentiable, this is like when we do this in English all the time. So I know not all languages do it quite like this, but we just change the verb tense, or we change how something's done in present tense or past tense or whateverable. Whateverable, that was not a word. We do that, right? So if it has a derivative, we call it differentiable. That's the word that means the same thing in different part of speech. There is an alternate definition of derivative, and I'll talk about how this is different. It sort of looks the same. It says the derivative of the function f is the function f prime, given by f prime of x, equals the limit as h approaches 0 of f of x plus h minus f of x over h. Does that all sound the same? Almost. What's different notationally in this description than the last one? Yeah, this one has an X, the last one had an A, okay? And you might say, like, who cares, it's just a letter. Well, it means something slightly different. We'll get there. This one then says the domain of f is the set of x's for which this limit exists. The process of computing the derivative is called differentiation. There's that word again in a different tense. Further, f is differentiable on an open interval I if it is differentiable at every point in I. Quite a bit of writing on this slide. Jot that down, and then I'll talk you through the actual differences that we actually see in the definitions here. Okay, the first definition was very specific about the location where we were finding the derivative. It was at A. A was a specific number. We were given a very, very specific piece of information, and we only cared about that one point. Okay? This definition says, well, we can do that generally speaking everywhere that we have the ability to use a value of A. So any value I have of A that actually works, we could do this for. So this definition is sort of like more broad than the first one. This one's saying that first definition was very specific to this one location, but really it works everywhere as long as I am actually able to find a derivative at that value. Okay? Now, this definition is actually probably the one that's a little bit easier to use, and I'll show you why when we do an example, so that you can see the difference in it. Okay? Is everybody, you're still writing, Samuel? Okay, I've got a couple people still writing. I'll pause. Okay. Last time, when we had a problem like this, first of all, it didn't say derivative. It said something like slope of the tangent line. We were told an a value that we were going to do this at, right? We were told something like at a equal to 1. So when we created our problem, the a value in our problem was actually 1 plugged in all those places. This problem does not say that, does it? It actually just says, generally speaking, find the derivative. And I know some of you are looking at this and you can tell me like that what the derivative is, and I promise we'll do that in 2-3. But we're going to build up to that. So slow down for just a second with me, okay? By definition, that is this definition, the way we find a derivative is we use this limit process, okay? When we get to your test, I know we just finished test 1, but when we do get to your test over this material, you're going to do one problem like this for me, just one. Okay, so we're not going to belabor this point and do a whole test on this or something like that. We're just going to do one. But for right now, that's what we're going to look at is how we go about doing that. So what this says I should be finding is I should be finding f prime of x equal, which equals the limit as h approaches 0 of f of x plus h minus f of x over h. That is the definition of derivative. Okay? And we saw that last time, just we didn't have the x in there, we had a number in there. All right, so this means every step I'm going to have limit h approaches 0 on it. We don't remove that notation until we plug in 0 for h. And why can't I plug in 0 for h already? There's an h in the denominator, which looks an awful lot like a test question you had, right? That's why. Okay? Now, I know what f of x is. This second piece of information right there, I know it. What is that? Yeah, that's what was given to me, right? X cubed plus 2x plus 1. That's f of x. So if you think about taking this equation and filling in the piece you know is actually here at the end. It's x cubed plus 2x plus 1. The other thing that you know is that the denominator is h. So these pieces of information you get almost for free. They're just given to you flat out. The only piece that you have to work for is this first piece, f of x plus h. That's algebra notation. I'm working with my son in high school in Algebra 2 right now, and he's seeing this notation and he's not liking it. So there may be some of you who also don't like this notation. But all this notation says is, take your function, and everywhere you have an x, replace it with x plus h. Okay, so I've given this function right here, and it has some x's in it. And everywhere that function has an x, I'm going to replace that x with x plus h. So that's the first piece, x plus h cubed. The second piece is 2, and then it's x plus h. And then the piece at the end, 1, is just 1. I don't have to do anything for that. So all of that comes from f of x plus h. And when you look at that, that should just scream at you, I've got a lot of algebra multiplying things out, foiling and distributing and stuff to do. Is that what it scream at you? Maybe those weren't the exact words, but more or less? Okay, it should. And you do. It's actually a correct screaming of your mind. That's exactly what's going to happen next. All right, so you're welcome to get a scratch piece of paper to multiply some of these out if that helps you to think about it a little bit more clearly. I'm going to multiply out my x plus h times x plus h times my x plus h, just right up here. This is not x cubed plus h cubed, right? There's a tendency to love, we would love that to be true. Man, that would be so friendly, wouldn't it? But it actually doesn't work. It's not correct. If you try to make that work, it won't work. So when I'm looking at this x plus h times x plus h times x plus h, I'm going to take two of them at a time. So I'm just going to work with these two, and we're going to multiply these two together. So we multiply the first terms together. X times x is x squared. What happens when I multiply my inside terms and my outside terms? What is the...
2x.
Yeah, I get an xh on both of them, right? xh in the middle, xh on the end. So Josh is right. I'm going to have a 2xh. And then the last terms, h times h, give me h squared. Now, unfortunately, we're not done because I still have to multiply that result times x plus h, right? Okay, let me see if I had another slide put in here. I do. Let me do this on this other slide so that I'll have just a little bit more room to work. Okay, so the next thing I'm going to do is I'm going to actually multiply each of those x squared, 2xh, and h squared by the x and by the h. So I'm going to multiply x squared times x, which is going to give me x cubed. And then I'm going to multiply the 2xh by x, and that's going to give me 2x squared h. And then I'm going to multiply the h squared times x, and that's going to give me, you can either write it as h squared x or as xh squared, either way, right? It's the same stuff? Wonderful. All right, we're going to do the same thing again now. We're going to multiply things by h. So now I'm going to multiply x squared times h. What's that going to give me? X squared h, or hx squared, either way. Then I'm going to multiply 2xh by h. What's that one give me? 2xh squared, good. And then the last one, h squared times h gives me h cubed. Excellent. Now, x cubed is the only x cubed in there. But what else do you see? Things that sort of go together.
X squared H.
X squared h
2x.
goes with the 2x squared h. You guys good with that? So how many x squared h's do I have? I have 3 x squared h's. What else do I have? The x squared h and the h squared x. Right? H squared x came first, and then the x h squared came second. I'm not even sure if I said it right. Anyway, the ones that are double underlined, they match, right? Same variables, same exponents on those variables. So how many of those do I have? 3. And I'm going to write my x first just so that they're in the same order as the other one. That doesn't make any difference, but just for the order to be the same. And then I have h cubed, right? All right, so this is the same thing that I have. That was not what's supposed to happen. It didn't work that at all. Let's try it again. X cubed plus 3x squared h plus 3xh squared plus h cubed is equal to the x plus h quantity cubed that I had to begin with. There's my piece. That's not all I had. I mean, that's this piece only, right? That's all that is. That's all I did was just write that piece only. The other pieces are easier, though. The 2 times x plus h, what does that look like? Thank you. 2x plus 2h. And then I have that plus 1, right? If you would like to distribute the negative, you can. I'm going to leave mine as minus whatever comes next, and I'll explain why in just a second here. Okay, so everybody have some version of this that matches, at least the actual values match? Okay. The reason I leave my part at the end in parentheses is because everything in that parentheses cancels with something before it. It matches something before it, identical with the opposite sign, because we have a negative sign happening right here. Okay, so do you see the corresponding 8x cubed from the first set and the second set? Yes, right here and right here, those add to 0. Do you see the corresponding 2x in both sets? Yes. This one and this one add to 0. And do you see the corresponding 1 in both sets? Here, and those add to 0. So 6 pieces of information just added to nothing, right? That means I've got a lot less to work with than I did before. Not only that, but I would like for you to take a look as you rewrite. Don't say anything out loud. Give everybody a chance to look. Tell me, in your head right now, what you notice in the numerator happening now. In your head. Okay, now say it out of your head. What do you notice in the numerator? They all have H's in them. Do you see that? That has to happen. If that didn't happen, you made an error. There's something that happened incorrectly somewhere along the way. So make sure at this point you've got an H in everything. Why does it matter? Well, because I need that H in the denominator to go away, right? Okay, so if you take a look at the numerator, our next step is going to be factoring an H out of the numerator. So we're going to take that numerator and we're going to factor an H out. So that gives me 3x squared. It gives me 3xh. It gives me h squared. And it gives me 2. All over the same h as before. At this point, it looks like that radical problem from your test. At least your test should have gotten to the point where it looks like you had an h, or in your case it was an x on that problem in the numerator, and an x in the denominator, and they were able to factor out like this and cancel. That's exactly what we're going to do with our h. This h divided by that h is 1. Right? That's what reducing does, is it divides out common factors. So what am I left with? Well, nothing in the denominator. Like, that's the important part, right? I don't have a 0 problem anymore. I have 3x squared plus 3xh plus h squared plus 3. And what am I able to do now that I could do in no step before? Oh, did I make the problem? Oh, that's what happens when you can't read your own handwriting, isn't it? Not good. Sorry. Let's write that 2 as a 2. Okay. Jacob, you had said, what am I able to do right now that I was never able to do before? You got it. I'm able to plug in 0 for the h, right? So everywhere I have an h, I can actually plug in the 0. So this would actually be 2, not a 2, 3 x squared. There's no 0 there. 3x times 0 plus 0 squared plus 2. And what does that equal? 3x squared plus 2. Okay, so pause for me, those of you who have taken calculus before. Look back at the original problem. With the simple rules and things that you remember from when you had calculus once upon a time. Is that correct?
Yes.
Yes, it is. Okay, and everybody's about to know the simple rules, so then it won't look like we just did magic. You'll know it too. So, but yes, this is correct. Any questions on this one? Okay, we're going to do another one, and the one that we're going to do next has a radical involved. Because radicals are cool. So, as we do this radical problem, you're going to notice it's going to feel an awful lot like some problem you had on some test somewhere recently. Okay? So think through this problem as you go back and look at redoing that problem on your test for those of you that affects. All right, so we're going to start the problem out the same way. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. This one's actually easier than the last problem because I don't have to cube anything. That's good. You thought there was radicals and made it harder. It actually is going to make it easier on this one. Okay. So do you have an f of x function given to you? Yes, you do. So the part at the end is the part that I can automatically plug in exactly as it was given to me. So that's the square root of 4x minus 2. and I've got the h on bottom. All of that is an immediate result of what I know about the formula, okay? The first part, again, says, take the function. Everywhere you have an x, put an x plus h. So on this one, it's still going to have a square root. I'm still going to have a 4. And instead of having an x, I'm going to have an x plus h. And I still have that plus 2 underneath that radical. I mean, it doesn't go away. Okay? The 2 doesn't... Oh, it was a minus 2. All right, well, we'll make it a minus 2 then, if you insist. Okay, does that look all right to everyone? So far, so good? Excellent. All right. Let's simplify underneath that radical. This is 4x plus 4h minus 2 underneath the square root minus, I've got another square root over here, 4x minus 2 all over h. It's not a very exciting step, but nonetheless, we can do that. Radicals involved. What do we have to do when there's radicals involved? Have to multiply by the conjugate. Okay? So the conjugate of this, well, the conjugate looks pretty much the same. I've got the square root of 4x plus 4h minus 2. And I've got the square root of 4x minus 2. But what goes between them? Yeah, the opposite sign. Previously I had the minus sign, so I'm going to have a positive sign. And if I multiply this on the numerator, I also have to multiply it in the denominator. Right? Right. Now, the denominator, a couple of you did this on your test. You tried to distribute the denominator. We don't want to do that. We want to leave the denominator factored. We really do. So we're going to rewrite our denominator here exactly like it already appears with that h in front and that square root right beside it. Okay, so that's my denominator. The numerator becomes very, very, very nice. The whole point of conjugates is that the inside terms, when you multiply them, and the outside terms, when you multiply them, are the same value, but what? They're going to be the exact same, but what? If I try to multiply these two and I try to multiply these two together, I get the same thing except what? Opposite signs. The outer one, right? So the first square root and the very, very last square root, the big outer, blue markings that I have there, that's positive. The ones that are in the middle are negative because of the sign on the first one's negative. But otherwise, it's exactly the same. So what happens when you add things that have the same value but opposite signs? They cancel. That's what we actually call a difference of squares when that has the ability to do that, is that it cancels out the inside and the outside because they add to 0. Why is that valuable? Well, because what happens when I multiply the other two pieces? That is, what happens when I multiply the first terms together?
4x plus 4h minus 2.
I get the exact same thing but without the radical. And that's actually what I'm really wanting as I work through this problem, is to eliminate the radical in the numerator. Now then, let's do the last terms together. What happens when I multiply the 4x minus 2 underneath the radicals together? I get 4x minus 2. And it's negative, right? So it's like minus 4x minus 2 like this, because it is a negative. I have one negative and one positive, because I've got this negative sign right here and this positive sign right here. Fantastic. Now look at that numerator and tell me something beautiful that you see happen. Much of it cancels. So, does the 4x cancel? Yes, ma'am. Does the 4h cancel? No. Does the negative 2 cancel? Yes. So what's left in the numerator? 4h. That's like a farming thing, right? 4h? Yes. Okay. And I'm just rewriting at this point. Okay, now what do you notice? That h cancels. That's really what we wanted to happen, wasn't it? Really is. So let's take just about 2 more steps to finish the problem out. Right now I have the limit as h approaches 0 of 4 on top over the square root of 4x plus 4h. Was it plus 2? Minus 2. Minus 2. And then I've got plus the square root of 4x plus 4h. I'm sorry, plus minus 2 again. There we go. In the denominator. What can I do that I couldn't do before? I can plug in 0 for my h, right? Okay, so the 0 comes in right here. So I'm going to avoid writing all that out with the 0 in. I'm going to condense a little bit as I go. The first radical is 4x minus 2. Plus the second radical is 4x minus 2. Now what? Yeah, there's just 2 of them in the denominator, right? This is 4 over 2 square root of 4x minus 2. Now what? The 2 and the 4 will reduce. What will that become where? 2 on the top. Good. Now, this is actually completely done. Some of you are going to feel bothered by it, so tell me why it bothers some of you. There's a radical in the denominator. So let me tell you why this is done. When you saw radicals in denominator in trig and you were always rationalizing, the radicals you always saw were radicals of just numbers. Think about it. If they were like square root of 2 or square root of 3 or something like that, it wasn't variables in there, right? We rationalize the denominator when the denominator is not rational. Well, this denominator, we don't know if it's rational or not because it depends on the value of x, right? Are there some numbers of x that I could put in that would make this value actually a perfect square root? Yeah. So we don't rationalize anything because we don't actually have anything irrational at the moment. We have the possibility of irrational, but not necessary. So the problem is actually finished at that point. Okay. I want you to give you a little bit of notation, alternate derivative notations. All of these mean the same thing. It doesn't matter to me which one you use, but you do need to recognize when you see them what they're asking. In particular, for instance, if you see dy dx, you need to know that just means derivative. That one's very commonly used. Most of us tend to use one of these first two, either f prime or y prime, as we're doing our work. That's great. These last two are not used quite as frequently, but they are occasionally used, in particular in your textbook, df dx or d dx of f of x. The notation here in the middle is very friendly because it reminds us of slope, y's over x's, right? And this is also a slope of a tangent line. So that's kind of friendly notation to remind us of that feature. All right, the last thing in this section is about sketching graphs. So we're going to start with sketching a graph and talk about how we sketch graphs of a derivative. And this will be when we don't have a function given, like we don't have an equation. It's usually where this happens. The goal of sketching a graph in f prime is to begin with a graph of a function and draw a graph that represents the derivative, i.e. the slope, at every point. In general, we want to observe the slope of the graph at some important points. So specifically, what are the important points? Well, we find where the slope is 0. We find where the slope is positive or negative. And sometimes we do number 3. We note how the slope is changing. So we're always going to find where the slope is 0. We're always going to take a look and make a decision about where the slope is positive or negative. And sometimes we're going to think about, is the slope becoming more positive or less positive or more negative or less negative, and make those kinds of claims. All right, so let's take a look at an equation, or graph of an equation. I think the A and B is marked on your paper. If it's not, go ahead and mark those. It should look like A is at this sort of a peaking value, a maximum value, and that B is sort of occurring at the X value of the minimum value. Yes? I'm sorry. Noting how the slope is changing. How the slope changes. I forgot that I hadn't typed all those in there for you. I'm sorry. Take a deep breath. Slow down just a little bit, Dr. Hands, right? Okay, do you guys have that one written down? Are we okay to try one? Okay. This is a graph where I've got a peak at the X value of A, and I've got a valley or a minimum at the X value of B. Everybody good so far? All right. So what we're going to do as we do these problems, and you're going to do this on every single problem, is you're going to make a list of those specific things that we want to know. We want to know where the graph is 0, where the slope of the graph is 0, and how the slope, whether it's positive or negative at different points. So we're going to first start with this one, and we're going to write down this statement right here that says slope is 0 at. Where is the slope of this graph 0? A and B. And remember, we're talking about slope of the tangent line. If I were to draw tangent lines at A and tangent lines at B, they'd be horizontal, right? They'd be flat. So the slope of those two lines would be, each of those two lines would be 0. What we're going to do next is we're going to take a look at how the slope is changing based on the sort of intervals of the graph. So let's take a look at this piece of the graph before A. What can you tell me about the slopes if you're moving from the left until we stop at point A? They're positive. The slopes are positive, right? If I drew my tangent lines, they would all have a positive slope. So we're going to say that the slope is positive from negative infinity to A. And I'm using parentheses because at A itself it's 0, so I don't want a bracket there. I want a parenthesis there. The next piece of the graph is going to go from where to where? A to B, because something different happens between A and B. What in the world happens between A and B? Right, my slope is negative from A to B. The last piece of the graph, what is happening? The slope is positive from B to infinity. This is actually enough information to get a graph. So I'm not going to have to do step 3 on this one. I'll let you know. Usually you have to do step 3 because you don't have a lot of information from steps 1 and 2. We've got a lot of information in steps 1 and 2. So over to the side of this one, I want you to draw an XY axis. The XY axis needs to look very similar to the XY axis you already have, especially the X values. In other words, the A and the B need to look like they're in about the same location that they were before. Okay? A and B in roughly the same place. The next thing you're going to do is if you have a pencil or a pen with you that is not the one you're currently using, it's a different color or like a pen instead of the pencil, grab it out. That's what I want you to grab. If you have colors, that's awesome. Purple, red, green, whatever, okay? If you don't, just use a pen or a pencil that's not what you have. And if you don't have an option, just use what we've got. What I want you to do next is I want you to go back and I want you to take the word slope everywhere and I want you to mark it out. And instead of the word slope, right on top of it, I want you to write y value. 4 times. Y value, y value, and y value. When we made all of our claims initially, we made the claims about the slope, right? Everything we wrote down was about the slope. What we're going to do next, though, is we're going to draw a graph where the y value is doing these things. So let's try the first one. The first statement now says the y value is 0. What in the world does it look like when you have a y value of 0? It's on the x-axis. It's an x-intercept. We're crossing that graph, right? So over here on my graph, I'm going to put a point on the x-axis at A and at B. Because that's what it told me to do. It says I have a slope. Originally, I had a slope that was 0. Now I have a y value that's 0. All right, the second one, the first piece of the second one says, y value is positive in front of the value a, right, to the left of the value a. What does it look like to have a positive y value? Not slope, y value. It's what?
Above the x-axis.
It's above the x-axis, right? Positive y values are above the x-axis, negative y values are below. So before the value of a, I need to be above the y-axis. And there's nothing with what we're doing. This is a sketch. So does it look straight? Does it look curved? We don't really have a way of describing that exactly at the moment. But we just need to make sure that we do need it to cross the x-axis or the y-axis though, because the original graph did. Did you have a question, Snyder?
No.
Okay. We're okay? What happens between A and B? The y value is negative, which means what does it look like? It needs to be below the y-axis. But not only does it need to be below the y-axis, but it has to connect the dots I've already got, right? Let's connect the dots like when you're little kids at the Chili's and that kind of stuff, right? You're going to connect these dots right here, beneath the graph, underneath the graph. And then what happens after the value b? Positive y values, which means I need to be above the graph again. So this would be a sketch of what this would look like. We're going to try another one. Now, this one is not marked as the minimum value, and you need that there. So give that little marking a little home and give it a name. What letter would you like to put there? Z. Really? Oh, C. All right. C sounds good. We'll do C. I mean, Z would be okay as well, but all right, C. All right, so let's do the same thing we did before. Step number 1, tell me, where is the slope 0? Yeah, the slope is 0 at C. Step number 2, tell me what is happening as you move from left to right. In other words, from the far left of the graph, negative infinity, until I get to the place where it changes to 0, what happens? It's negative. The slope is negative, right? The graph is decreasing. We're not using the words increasing, decreasing. That is extremely unhelpful information right now, actually. The slope is negative. And then I have another place afterwards. The slope is what? What happens to the slope after C? It's positive. And actually, again, this is enough information to give us a sketch of what's going on. So we're going to draw our xy axis, much like it was already drawn before. We're going to mark the C value in, roughly the same location it was marked before. And then what are we going to do with our other colored pen or pencil? We are going to mark out slope, and we are going to write in y value.
Is that something you want us to do on our homework?
I would like for you to do it on your homework. It's really for your benefit to remind you to not draw a graph that's doing something about the slope. Yeah. All right, so going through this, the first one, y value is 0 at C. What does that look like? An x-intercept, right? I'm going to cross the x-axis at C. What's happening before C? What's the y value? It's actually negative, isn't it? So it means it needs to be where? Below. And I'm not told how by the descriptions that I've got. Could it look straight? Sure. Could it be some kind of a curving feature? Sure. It actually depends a lot on the actual equation of the graph, and we don't have that actual equation. So if you want to draw it straight, that's cool. What's happening after C? I should be above the axis, right? I need a positive y value, so I'm up here. So this would be one example of this particular graph. Number 5. Use the graph of f to sketch the graph of f prime. Same directions. First issue. What can you tell me about the slope being 0? Good. The slope is never 0. That's important information. It doesn't let us mark anything on the graph, but it lets us know something that won't be marked on the graph. I won't have an x-intercept, okay? What can you tell me about the slope that is happening? Good. The slope is positive everywhere, from negative infinity to infinity, always. Any of that would be fine. The slope is always positive. There's another feature about the slope, step 3. Step 3 is supposed to be talking about how the slope changes. It doesn't. This slope is constant. It's exactly the same everywhere, right? So the slope is, you can write the word constant, or you could write the phrase is the same from negative infinity to infinity, or everywhere, or something like that. Believe it or not, as little information as that feels like, it's plenty enough information to draw the graph. What do I still need to do before I can draw the graph? Mark out slope, and we're going to write y value. We already talked about what number 1 means. The y value not being negative means I don't have any x-intercepts. The second one, the y value is positive. What does that mean? I'm always going to be above the x-axis, okay? So I'm not going to have anything underneath the x-axis. What does it mean for the y value to be the same everywhere? It's horizontal is the word I want. Yes, it's a horizontal line. This will be a horizontal line above the x-axis. And again, I don't know exactly how far above. It's not really the point. But it is above the x-axis. Okay. We'll do one more, and then we'll pause, and we'll talk about my schedule and the board being all out of whack again. Because that's what happens. That's what I do. All right, this one. What can you tell me about this y value being, or sorry, the slope being 0? It's not, but is it like almost 0 somewhere? That's useful information, so we can say the slope is almost 0 where? You could say on the left, or as x approaches infinity, negative infinity. So as x approaches negative infinity, that means the left-hand side. What can you tell me about the slope being positive or negative or that kind of stuff? The slope is always positive, right? Now, what can you tell me about how the slope changes? All right, so on the far left, the slope is pretty flat, isn't it? And as we move over here, this line that we keep drawing, this tangent line, becomes very, very steep. Do you guys see that? That's actually telling me something about how the slope is changing. So the slope becomes more positive. You could use the phrase increases if you'd like. As x approaches infinity. That is on the right side of the graph. Let's change these all to say y value. And let's sketch that graph really quickly. What does it look like to have a y value that's almost 0? Where are you if it's almost 0? You're right. You're really close to the x-axis, right? You're almost on the x-axis. So I need to be really close to the x-axis over here somewhere. I am always above the x-axis. Why, Cooper? Because it said the slope, or in this case now the y value, is always positive. And my y value needs to become more positive as I move towards the right. What does this graph look like? What's it look like? Somebody said it. What is it, Josep? It looks the same. This graph looks the same as its slope graph. Now, it may be more steep or it may be a little bit less steep. We don't really know that. But the overall shape is the same as the original one I started with. The y value and the slope are doing the exact same things in this graph, which is unique, and we will not see that happen. And why? Until Calc 2. Man, what a cliffhanger, right? Okay.